Welcome to this lecture series in linear algebra. Let us recall some of the things that we need to follow this lecture. So suppose V and W are vector spaces over a field F and S and T are linear maps. Then S plus T is also linear, and the definition of S plus T is given by this thing. So it takes any vector here to this value. Similarly, if T is any linear map, then the scale of T by alpha, so to say, alpha T as we write it, is this map. And this is also linear. And all these two things are very easy to check. We discussed this earlier, but one can check them now if we didn't do them earlier. All right. Another important thing that we need to discuss is the following. Let V and W be vector spaces over a field F. Let this be a basis of V. And now if phi is any map from the set whose vectors are precisely the basis vectors, the basis chosen, if phi is any map, then there is a unique linear map T from V to W, which behaves the same as phi on the basis vectors. So diagrammatically, suppose phi is this map, and this is the inclusion map. What does that mean? It means it just picks a vector here and sends it to the same vector above. This makes sense because this is, after all, a subset of the above thing. So that's how this map is behaving. And the statement says that there exists a unique linear map T such that this diagram commutes. What does that mean? It means whether you go this way or you go that way, it's the same thing. Also, this notation you must be familiar with. This is there exists, while this exclamation mark means unique. So there exists unique T. So writing this yellow thing or making this diagram is precisely the same. We stated this fact not quite this way, but it was exactly this thing. We wrote it in a different fashion, but I'm writing it differently now. Okay. These are the problems. And now let us get started with the material of this lecture. So let me quickly define a vector space structure on Hom VW. So V and W be vector spaces over a field F. We equip Hom VW with two operations. The first is the addition operation, which takes a pair of linear maps to their sum, and we just discussed what that means, what this sum means. And the other is the scaling operation, which takes a scalar and a linear map to the scaled linear map. And it is a straightforward exercise to show that this quadruple is also a vector space. So out of two vector spaces over a common base field, we have constructed another vector space. Now the interesting question is, if these are finite dimensional vector spaces, and we will always assume that when we use the phrase vector space, we will always assume that we are discussing finite dimensional vector spaces unless explicitly stated otherwise. So if V and W are finite dimensional vector spaces with dimensions whatever, what can we say about this guy? Is it a finite dimensional vector space? And if it is, then what is its dimension? And the next theorem answers this question. So here is the theorem. The dimension of the space of linear maps from V to W, which is a legitimate vector space as we just commented, is the product of the dimensions of the participating vector spaces. So it is a beautiful statement, a very simple one, not contrived at all. And the proof is also pretty simple. But we need to perhaps discuss the intuition behind it, maybe. Let's see. So we'll see that as we go along. So let this be a basis of V, and fix a basis of W. All right. So that dimension of V is M and dimension of W is N. And now here is the intuitive idea. To define a map from V to W, all we need to do is choose a map from this set to W. Right? This is what we just discussed. Defining a linear map from V to W is exactly the same as finding a map from this set to W. And now the question is, how, what are the ways and how do we encode a map from this set to that? So basically what we need to do is we need to pick M vectors in W. And to pick a vector in W, all we need to do is find N scalars. So for each vector, we have N scalars. So total of m times n scalars is what we need. And this is where this number m times n is coming from. So that's roughly the intuition. And now let us execute that. So for I in 1 up to m and j in 1 up to n, define a linear map Tij from V to W, which is defined as Tij takes Vk to Wj if k is equal to I and 0 otherwise. So Tij gives special treatment to the ith vector in the domain and sends it to the jth vector in the target, jth vector in the basis chosen for the target. Everything else it just kills, sends to 0. So as a special example, T11V1 is W1, but everything else just dies. Okay, and here is the main claim. So we claim that this tuple is a basis for Hom VW. And clearly this will suffice to imply this equation. Okay, so how do we do it? We need to do two things. First is linear independence, and the second is spanning. So for linear independence, what we need to do is we need to show that if we pick scalars such that the corresponding linear combination is 0, then the scalars to begin with must be 0. So suppose alpha ij for I and j in this range are such that summation ij alpha ij tij is 0. Want to show that alpha ij is 0 for all I and j. This will imply linear independence. Okay, so fix a k in this range. Then clearly summation ij alpha ij tij vk equals 0. Thus summation I comma j alpha ij tij vk equals 0. So again, just to highlight, this is a vector and this is scaling that vector. Okay, now let me do the summation in two parts. So j runs from 1 to n, while I runs from 1 to m. And let me put a bracket. So this is 0. And now the point is, this chi is 0 whenever I is different from k. So this summation is only meaningful when I equals k. So what we get is the thing becomes j equals 1 to n alpha kj, because if I is different from k, the thing adjacent to that scalar is 0. So alpha kj tkj vk, right, which is 0. This implies summation j equals 1 to n alpha kj, and now by definition of tkj, this is wj, this is 0. But now by the fact that w1 up to wn is a basis, this implies alpha kj equals 0 for all j. Right, but now k was completely arbitrary. K was chosen as an arbitrary element from that range. So this shows that actually each alpha ij is 0, and we are done. So this establishes linear independence of the chosen list. Now we need to establish the spanning property, which is also very simple. So let T in Hom VW be arbitrary. Want to show that T is in the span of the Tijs. So what we have is, let's say, let tvi equals, well, tvi is going to be some vector in the space W. So there are scalars wi1, wi2, sorry, alpha I1, alpha I2, and so on, such that tvi is summation alpha ij wj. Right? So basically, I should write, what I should really be writing is that, sorry, let alpha ij, I in this range, j in this range, be scalars such that this equation is satisfied. And there are unique such scalars. Please take a note of that. Okay, so just check. I will just leave this as an exercise for you to check that T equals this map. How do you check that? Just check this on each vector vi, or maybe I should say vk. So fix a k, just check that tvk is equal to that thing. So this is exactly the kind of exercise we just did in this part of the proof. So just, if you check that, it is clear that T is in the span of the Tij's. I'm being lazy and I won't write the indices, the range of the indices. And this finishes the proof. So spanning property, maybe I should also make that heading. This was the proof for spanning property. Right. So therefore, the claimed list is indeed a basis. This is a basis for the space of linear maps. And therefore, we have this very nice theorem about the dimension of the space of linear maps. And with this, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.